This segment is on computer graphics. As we discuss some of the terms about how visual images are represented on a computer, it should help us better understand how we can control those images and create them in the first place. Whenever we view graphics on the screen, we are viewing a simulation of images presented on a monitor, probably our computer monitor. So even the letters that we use to make up the word graphics are actually just simulations or drawings on the screen that represent those letters. If we blow those up, we start to get into the nature of how the screen actually represents those images. Pixels are the small points on our screen that can either have a black or a white value, and in the color world can have multiple colors assigned to them. When we look at an image that's been blown up like this, we say it looks pixelated because we see the square nature of the little blocks of pixels. So our screen is made up as a grid, a bitmap is what it's called, of small squares, and as we fill them in, we start getting an image, like the beginning of this leg of the letter A. So the screen sees each of these grid pixels as a numeric placement on the screen. So 0, 0 is the top left-hand bottom or top of our screen, and going, depending on the size of our screen, down to some large number in the bottom corner. So as we look at this image, as it's represented here, 0, 12 is the first placement of a black pixel. Everything up to there is white. Then we would go to the second line and we'd start at 1 and go over to 111, which is the next black one, and then 112. So those would become the differences in that pixelated map or that bitmap of this image. So we're looking at this image. We already talked about it being very pixelated. This is actually a system that's called a raster system. This is a raster image because it's created by the use of pixels and the use of those coordinates, you might say, like 0, 12 or 1, 11, to tell the computer which to turn on black and which to turn on white. Therefore, to store that information, we have to store the information for every little teeny tiny pixel to gather that information and represent it on the screen. Now, one thing has been developed which is called anti-aliased images. So, at the borders where we go from one dark, perhaps black, pixel to a white one, we'll add in some gray ones along the edge. And if you'll squint your eyes and look at that, or if you look at it further distance away, it will look less pixelated. It's just an optical illusion. The pixels are still there, but there's a little more variation between the white and the black by placing some values in between. Here's another way of representing the letter A. This is not a rastered image, this is a vectored image. Quite different. The way it differs is the fact that rather than writing down every single pixel and keeping track of what color it is, we assign an algorithm to this letter A and tell the computer to start at 0, 10 and draw a line down to 26, 0, and it does, and it creates the slanted line of the first part of the A. So we give that a formula in which to draw the letter A rather than to keep track of every one of those little pixels. This is a vector image. The nice thing about a vector image is because it's just drawing from one reference point to another, we can simply change those reference points and enlarge or shrink or create different shapes altogether. So, the letter A. And so, in a vector world, it's the same algorithm used over and over, and just changing the different coordinates to make a different size for the drawing. So let's compare these two worlds, because we need to know how to control them and when we're using one over another. First of all, something that's important to us is storage. Taking the information to recreate these store them somewhere so we can open them up again and view them again, or change them or do what we need to do with them. Let's get an idea of how much space of memory it takes to store a rastered image. So here's the letter A in its varying sizes, and you'll see as it gets larger, it obviously takes up more storage space because there are more pixels being used for the image. White and black, we have to store all those. In a vector world, we are simply storing an algorithm. So the differences between the small a and a large A are not as great. They take up less memory. So obviously, it might be best to have a vector image because larger or more information can be stored in a smaller space. But there are other advantages of a raster over a vector. Here are two rectangles. One's created in a raster world, one is created in a vector world. To you, there isn't any difference. But there is quite a difference if you want to manipulate that image. So let's say we would like to remove part of that rectangle. We use an eraser tool and we make a couple of swipes, and we have now altered that rectangle in a rastered world. And we can do that in a rastered world. We are simply changing the value of all of those pixels that used to be black to white and changing that image. We can't take an eraser and erase a vector. If I try to erase it, it simply shows me handles and asks me to adjust the algorithm by grabbing one of the handles and dragging it to make it larger or make it a different shape altogether. So which format would you choose? Well, it might depend on what you need to accomplish. Let's say we're doing a costume design. This is a fairly involved image, and we want it to look fairly natural. We want it to appear drawn, a little more fluid. This might be very hard to recreate geometrically. It probably could be done, but it would be very difficult to draw it using vector tools that think geometrically. So this image is more than likely created in a rastered world. Here's the scenic floor plan. It's more geometric. You can probably see that it does consist of line drawings. Therefore, mathematical equations could tell us how to redraw this. So this is a vector image. Here's a light plot. I'm sure you're already guessing. Yes, this is a vector world again. Each of those symbols for those lights is reproduced very quickly with even the lettering. Everything just kind of turned this way or that way. A little bit of a change in the mathematical equation, and we can draw this image. Again, more liquid, a little bit more like a costume design, a little more artistic, a little less predictable. Therefore, a makeup design is more than likely going to be a rastered world. Here's a sound block diagram. Again, rather geometric. We're going to probably guess, again, that this is a vector world. A scenic drop. Getting a little more involved, adding color, having a lot more art, a lot of variations in the colors, a lot of variations in the values. This is going to be best captured in a rastered world. Let's get it right. But there may be some images, such as this scenic schematic, that might have elements that are very geometric, but it might have other elements that are less geometric, more fluid, and therefore we might try to combine these worlds, in which we can do that. That is generally done by layering the image. We can't mix vectors and rasters within a layer, but we can make a raster and a vector layer overlap each other and therefore look like they appear in the same world, and we can therefore control the look of an image by having a combination of vectors and rasters. Here is a property design. More drawn, more fluid, again, more than likely a rastered image. Here is a furniture orthographic. This drawing is symmetrical, geometric, and while it has curves and a little art and maybe some highlights and lowlights, we would probably still guess, yes, this is the vector world. Here's a costume pattern. This could be done in either world, obviously. The advantage, perhaps, of doing it in a vector world is that it can be resized and adapted for different measurements. So, we've learned a little bit about rasters and vectors. We've learned about different types of theatrical images that might be best created in one over another, or combinations, perhaps. The next thing we need to understand when it comes to storage and use of these files is format. Let's talk about some formats that you probably recognize. There's TIFF, there's GIF, there's PNG, RAW, and JPEG. They're not in any particular order, but each one has a different size scale that will work with them. And more than that, they will probably tend to range in the vector or the raster world one way or the other, depending on the kind of storage that they do keep for us. Let's look at them each individually. TIFF. TIFF stands for a tagged image file. It's considered a lossless format. Lossless meaning that once you've captured it, once you've used it, it doesn't lose a lot of information. It's therefore high quality. But it's very hard to support it on the web because the web wants to work with small files. It takes a long time to load in a large image on the web. And TIFFs are therefore hard to email to someone. They're very hard to exchange back and forth in a quick format. But they do contain all the information you need to get a very good, sharp image. A GIF stands for Graphic Interface Format. This was created, quite literally, for the web. It's considered a lossless format, but it is a compressed format. So information that is not needed is removed. If there's lots of white pixels, they're removed. And it cannot index colors, so it can't get into all the millions of colors. It is regulated by 256 colors exactly that have a number or an index. And therefore, if I say number 23, that's the color it's going to be, always. This allows us to have images that look a lot like a TIFF, but are usable on the web. A PNG stands for a portable network graphic. This format was developed to replace GIF. It does a better job of allowing 24-bit color with a lot more, therefore, selection of colors, but it tends to be somewhat slow because it's a lot larger than a GIF file. It is considered a lossless format, and it's not as much compression. But again, it does take up a little more space than a GIF. RAW. Perhaps of all the formats, the best for quality would be RAW, because you're getting an image that is simply raw. It is all the full information. It's a photograph. It's a literal representation of the image. The hard part about it is any computer or any program has to interpolate the raw information into some other information, some other format, TIFF, GIF, PNG, JPEG, something, to be able to use it. It can't read a raw file. It has to basically translate it into a format that it can understand. So RAW is a great way to store an image that is a photograph that you want the highest quality of effect and look in its image, but it takes up lots of storage. It literally has to be a photograph. JPEG is probably the most popular there is. It stands for Joint Photographic Group. Obviously, it was therefore created for photography work and can do a fairly good job of simulating the photographic image. But it is a lossy compression in the sense that it does compress, it looks at colors and moves them to a color close to them that's easier to index. When you choose a JPEG, the computer will usually ask you what quality you want, a low, a medium, or a high. The lower you go, the more information you lose. And once it's lost, it's gone. You can't reproduce it. So remember that as you're storing different files in different formats. Let's now discuss input. You have to get the image into the computer before you can store it or use it. The most famous of all the input devices for a computer, of course, is the keyboard. Principally, it really talks basically the raster world of just steady one image type of information. The next input device that is the most used would be the mouse. This device allows us to do a lot more manipulation than a keyboard would. So many of us use a combination of the keyboard and the mouse in getting through most of our world. The mouse allows us to do a little more fine detailing and a little more precise image manipulation. There are other types of mice. There are cordless mice that can speak to your computer through the air, as it were, air mice. And there are some that have trackballs that allow you to have a little more precise manipulation of exactly where on the screen you want to move before you click or roll or manipulate an image. The next device that's becoming more and more popular is a tablet. Some device that simulates more closely the artistic pencil to paper feeling of creating an image. This one can work in combination with the mouse as well. But you'll notice there are often keys or buttons on the sides that allow you to have some manipulation or control over or enhancement to what you're doing with the pen. But the pen is allowing you to have the most contact with the image in which you're manipulating on the screen. This small Wacom tablet, while it is drawing an image, is not drawing directly on this appliance. You're actually drawing on the screen, so while you're drawing down here below on the tablet, it's happening up here on the screen. There are, however, other devices like the Wacom Cintiq screen, in which the image from the computer screen is brought right to the tablet. And now as you draw, you're looking at the tablet and drawing directly on that image. And there can be simulated obviously back onto the screen as well. But now you have direct contact with the image with a device that is made for image manipulation, more closely simulating the real art of drawing and coloring and painting. The scanner. The scanner allows us to take a picture of an image and turn it into a format. A TIFF, a JPEG, there can be other formats as well, but those are the most common because they are literally photographic type of images. This allows us to take an image that was completely drawn by hand onto the computer in a quick capture mode. I think most of us know now that photocopy machines now have built into them scanning capabilities. So you can scan an image on a photocopy machine, many of them, and either email that to yourself or send it through the web to yourself. But I'm guessing that more and more of us have these type of pocket devices that can also scan an image in a single shot using the photographic technique. Or we're seeing more and more digital cameras that can capture high quality images for us, and most of them are stored in TIFF or JPEG formats. Some for high quality work by photographers in RAW format. And even that little device in your pocket that you really use to talk to your friends is having more and more capability of capturing images for us at a better and a better quality every day. Once we have the image into the computer, we need to be able to get it out again. And while the world is inventing new and better ways to import images and input more information, they're also trying to find better ways of outputting. We know lots of different printer types. We have inkjet printers, we have laser printers, we have wax simulation, we have lots of devices for printing out and trying to capture what we see on a screen. And we're going to understand in a minute that that's a very difficult thing to do. We can always take it down to someone who might own a larger printer that has more capability and can better represent the image on the screen. And sometimes some of these copies can be rather expensive. We can also change their size and their scale so that they can be very large if we have access to a plotter that can actually reproduce these images for us. We have to remember that a computer screen is also an output. Your screen is not a computer. It is a representation of what the computer is doing, and it's your visual interface between yourself and the computer. We are taking that computer screen now and moving it into new worlds that are touchable, not unlike the Cintiq screen. So I can now interface directly with my computer by touching it and moving things around. Your phones are also now becoming touch screen, so you can manipulate back and forth without a mouse, without a keyboard if you want to, as the one on the left shows. So all of these devices are making it easier and easier to input and output information to a computer. We want to lastly discuss color because it's very important in understanding the interface that we need as theater designers. RGB, CMYK. I'm guessing you've heard those terms before. RGB stands for red, green, blue. CMYK stands for cyan, magenta, yellow, and because we already used the B, we can't use the B for black, so we use the last letter. Yes, K stands for black. These are two different color formats that are used in printing and in monitoring or representing or outputting what we're doing on the computer. Computer monitors are all RGB, just like your television. If you adjust the color on your TV, you're adjusting the red, the green, and the blue. These are the three primary colors of light. Now I know most of you might be saying, wait, red, yellow, and blue are the three primary colors. Well, I'm sorry, that is in the world of print ink, and we're going to look over at the CMYK for that answer because you're looking at some of those colors over there. But in the RGB world, yellow is a secondary color. Look at the color wheels below and you'll see that yellow is indeed one of the secondary colors. And you'll see the yellow, the cyan, and the magenta represented in CMYK over in the secondary colors of the wheels below the RGB screen. CMYK, magenta, cyan, yellow, and black. Please look back at the RGB. You will note that the combination of all colors in RGB is white. In the CMYK, the combination of all colors is black. So in the world of paints and inks, we mix to black. In the world of light, we simply remove light, we'll get black. But by adding light and getting all the colors there, we'll wind up with white. These two worlds are somewhat difficult to mimic between, and that's part of the problem of input-output. We are looking at an RGB screen that is eventually going to have to be printed in a CMYK world. So though we may be picking or selecting CMYK colors on a monitor for a computer, always remember, they're only being simulated because the screen can only represent RGB. Here is an idea of the gamut, or the range of colors within each of these formats. So the visible color gamut that our eye can see is fairly large. The RGB color gamut, though, if we look at this representation, is a bit smaller than the full visible color gamut. The CMYK is the smallest, more concentrated colors in the very center of the gamut, you might say. And the Pantone, simply put, Pantone is a brand name of papers made by a art paper company, and they developed a range of colors that artists like to use. You see them whenever you buy mat board, whenever you buy any sort of craft papers. They're all made in the Pantone color range. We'll learn later on that as we look at a computer, it can simulate the Pantone color range, or it can give you the code for the Pantone color range, so you can actually represent a lot of your images in the true colors of papers by using the Pantone colors. And a lot of the paint companies today, house paints, represent their colors in the Pantone range as well. It's become a nice color standard. So, That makes you just a little dangerous. You know about visual communication using computers, but always remember the most important thing is that you are looking at a computer screen that is number one, raster based, and number two, it is RGB. Everything else is simulated. Remember that.